remarks? Thank you. I'm going to give a few remarks, and I would just like to, in addition to the fact that we're all together again, I think that we have a really interesting day ahead of us, afternoon ahead of us, and hopefully you guys all got some lunch and you're all, ready and raring to go. And so I would like to just go through the agenda briefly. So we had poster presentations from 12 to 1 while you folks were eating lunch. And now I'm going to make a few remarks, and then we're going to have some student oral presentations. And then we have 2 awards to give. We have a Mackenzie Mentorship Excellence Award, and then Dr. Anna Blakney is going to give us our keynote presentation. And then we'll pile out back into the posters to read some more posters, and then we'll have an awards event and some social time together. I can't forget to thank all of those organizations that have sponsored us. And so this includes Canadian Blood Services, the Neil Mackenzie Memorial Fund, Diagnostica Stago, Bayer, Grifols, and most importantly, the Naaman Vickers Endowment Fund. So we have a lot of activity on social media, so please feel free to pile into that if you are a social media user. And I would like to just start our student presentations. There is a People's Choice Award, so you can feel free to pay careful attention to what the students are saying, and then you can go in and vote for them. And the summer students need to complete their peer evaluations through the link by 4:30 today. And we're having our first talker, our first speaker is going to be Jasmine Malhi, who's going to talk about procoagulant virus surfaces. So Jasmine.
Hello. Hi, everyone. My name is Jasmine, and I'm a student in the Prydesdale Lab. And today I'll be talking about my research on protein complexes that form on the virus surface to initiate blood clotting. So the star of our show today is the coronavirus. And here we have the human coronavirus 229E or HCoV229E that causes the common cold. Like its closely related cousin, the SARS-CoV-2 virus, which causes COVID-19, it has a beautiful corona or crown-like structure that surrounds it, as well as a virus envelope. How some viruses get this virus envelope is by infecting our body's cells, and when they replicate within them, they go ahead and steal our cell's membrane and the associated proteins. This becomes the outermost layer of the virus. When these clotting proteins are present on the surface of the virus, they help the virus bypass the strictly regulated mechanism of blood clotting, and that results in a blood clot. So a protein that we're really interested in looking at is tissue factor, which is the red molecule shown above on the left. Tissue factor plays a key role in the blood clotting pathway. It forms a complex with clotting protease factor 7A and calcium to form the complex called 10ase. 10ase can activate factor 10 to 10A, which essentially results in downstream clot formation. 10ase can also participate in cell signaling through the activation of the PAR2 or protease activated receptor 2 to enhance infection. So to measure the virus-induced effects on clot formation, we use the clotting factor 10A as an upstream measure for what's happening on the virus surface. As we can see, as we increase the virus concentration, we see an increase in clotting factor 10A generation, which suggests that tissue factor activity is present on the surface of the virus and plays a role in factor 10A generation. Next, we looked at how clotting enzymes influence cell signaling mechanisms to enhance virus infection. We performed We performed a plaque assay and used a number of plaques as an indicator of how much infection there was. We saw the greatest increase in factor 10A and 7A to enhance infection. So that suggests that these clotting enzymes actually influence cell signaling to enhance infection. So finally, what we found so far is that highly purified HCOV229E activates factor 10. We also found that clotting proteases enhance HCOV229E infection of cultured cells. And finally, we hope to extend these technologies to find virus envelope tissue factor on SARS-CoV-2, as well as hopefully use tissue factor as a broad spectrum antiviral target. Thank you.
I'm sure Jasmine will be happy to take a few questions if anybody has any. Okay, thank you. Our next speaker is Kate Halverson-Colkin.
My name is Kate, and this summer I worked with Anna Herman in the Kizakadatu lab to develop immunomodulating polymer conjugates for targeting and treating glycocalyx dysfunction. Now, this is a mouthful, so today I'm hoping to provide some context and clarity. This research project is particularly relevant considering glycocalyx dysfunction is associated with diseases affecting 1 in 3 Canadians. So the endothelium is a single layer of cells which lines all blood vessels, lymphatics, and organs. Our endothelial cells have a combined surface area approximating that of 6 tennis courts. The surface of each endothelial cell is coated in a thin layer called the glycocalyx. The glycocalyx is composed of protein and carbohydrate chains, which make up a gel-like protective lining. The glycocalyx plays a key role in maintaining healthy physiological conditions by regulating blood flow, inflammation, vessel permeability, as well as cell-to-cell communication. However, the glycocalyx structure is fragile and vulnerable to high blood pressure, inflammation, and trauma. Under these conditions, the glycocalyx has been shown to shed into the vascular lumen, leaving behind an exposed endothelium. Deterioration of the glycocalyx has been linked to cardiovascular and kidney disease, diabetes, sepsis, stroke, and even transplant rejection. As follows, the protection of the glycocalyx may prove a promising target in the treatment of these diseases. This is where we hope to come in. So our aim is to develop an injectable therapeutic which will bind to the endothelium and mimic the natural glycocalyx structure, thereby restoring natural vascular physiology. Our proposed therapeutic includes 3 essential components: a targeting unit, a polymer backbone, and a glycocalyx mimic. This summer, I've predominantly focused on the targeting unit, which must have the capacity to bind the endothelium while also minimizing non-specific interactions. The targeting unit will be bound to a polymer backbone that can be modified to contain our final component, the glycocalyx mimic. The glycocalyx mimetic group will allow for rebuilding and restoration of the glycocalyx's structure and function. Thus far, I have chemically modified targeting units and utilized cell-based assays to evaluate their binding capacities. So if you would like to hear more about my preliminary findings, please come by and ask me questions at poster number 2. Thank you.
Anybody have questions about this work?
Yes, is it likely to be immunogenic?
Immunogenic as in
Well, yeah,
stimulating an
you put on
immune
the
response.
surface and it's going to be foreign to the body. Is it likely
Yes.
to be immunogenic? Is this an issue?
Well, we're using antibodies, which should be okay. But the R group you can see here, that should actually be kind of like a synthetic replica of what is already in the body. So hopefully it will not be immunogenic. Yeah, so it's really important that the entire
Thank you.
therapeutic is biocompatible. Yeah, thank you.
Thanks, Dave. Okay, next up is Marcus.
Hi, everyone. My name is Marcus Xu, and this summer I've been working in the Divine Lab looking at the effect of fatty blood on the quality of blood donations. Okay, so blood donations continue to save lives, and with the amount of blood donors in Canada right now at a decade low, it's critically important that we maximize the quality of these donations. However, recent research has shown that when red blood cells are introduced to a fatty plasma, also called lipemic plasma, there are increased amounts of rupturing in the red blood cells. This is at least in an in vitro setting. So we are interested in looking at if this rupturing carries over to a short-term dietary setting when we have more fats in our bloodstream, and if this affects the quality of blood donations. Okay, so to do this, we compared blood donations from donors on 2 separate days, 3 hours after eating. On one day, the donor ate a fatty meal, which was considered anything greater than 20 grams of fat. And on the other day, the donor ate a lean meal, which had to be no more than 3 grams of fat. So with a sample size of 10 donors, each donor donated twice, once after the fatty meal and once after the lean meal. Then I would analyze the donations using different metrics immediately after the donation and 48 hours later. So these tests included red cell deformability, which measures the red cell's ability to withstand shear stress, hemolysis, which is the amount of ruptured red blood cells in the plasma, also osmotic fragility, which plots the red cell's ability to withstand different saltwater concentrations before rupturing, and morphology, where a microscope is used to analyze the quality of blood based on the shape of the cells. We also measured samples for the amount of triglycerides, which are the main components of fat, to ensure that the fat levels indeed varied in the blood between meals. So what do we find? Well, fatty donations are statistically different from lean donations in 2 metrics, but these metrics are only seen after 48 hours. So these 2 metrics that are significant, statistically significant, are greater osmotic fragility in fatty donations. So that means fatty donations have more rupturing at the same saline concentration, and higher levels of hemolysis in fatty donations, meaning there are more ruptured red cells that end up in plasma in these fatty donations. So with that said, this was a small sample size of 10, so certainly future research could expand on these initial findings to include more donors. As well, just because these results are statistically significant, whether these differences actually translate to clinically relevant differences is another area that should be further studied. And moving forward, we have frozen samples and plan to investigate potential changes to the metabolic pathways of these fatty and lean blood samples. Thanks for your attention, and thank you to everyone at the Divine Lab for their support. And if you'd like to know more, please stop by at poster number 4. Thank you.
Questions?
I'm wondering, hi Marcus. So I'm wondering what explains the presence of the difference only after 48 hours and not immediately? Like what's the main hypothesis there?
Oh, that's an interesting question. I don't know exactly, but I would have to guess that it just takes some more time for the fatty component, the triglycerides, to actually cause the lysing, and it immediately after. I'm guessing it just hasn't had a time to take effect yet. Thanks. Anyone else? Thank you. Oh yeah.
Is the 48 hours the time that's used in actual clinical use?
Yeah, the reason we picked, that's a good question, 48 hours is because 48 hours is the expiry time to, I guess, not package, but treat the red blood cells, so, or sorry, the blood. So they're separated and additive solutions are added, but after 48 hours, it's like expired. So that's where that number comes from. Thanks.
Okay. Melody, over to you.
All right, hello everyone. My name is Melody, and I'm very excited to introduce you to the quality improvement project I've been working on this summer. I had the pleasure of working with Dr. Andrew Shi, who is the Medical Director of Transfusion Medicine, Vancouver Coastal Health, and his team. So my project is a bit different as it doesn't involve wet lab work behind the bench. Instead, I look for trends in patient chart data to better understand the efficacy of how the current calcium administration system at Vancouver General Hospital improves trauma patient outcomes. This paves the way for better quality trauma patient care in the future. So I will provide some background information before diving into the project methodology. All right, so as some of you with a medical background may know, calcium is a component required to catalyze blood clot formation, also known as coagulation. It converges on the biochemical pathway over here, and coagulation is important to cease bleeding in trauma patients who already lost lots of blood to establish a state called hemostasis. On the other hand, blood is stored in a citrate-based anticoagulant, which is helpful as it prevents blood clots from forming during storage. Citrate is a good anticoagulant because it binds to calcium, so blood basically can't clot. When trauma victims come to VGH, large amounts of blood may need to be transfused in something called a massive hemorrhage protocol. But once this blood is transfused into the body, citrate still binds to calcium, so the patient's blood becomes low in calcium or hypocalcemic. This makes it harder for the blood to clot and also increases other physiological risks for the patient. So usually hypocalcemia is treated once detected, but a more preventative approach is being tested with a calcium flasher system consisting of reminders in packs of blood used during massive hemorrhage. VHH adopted this system in late 2019, which reminds physicians to deliver calcium whenever blood is given to prevent hypocalcemia later on. As you can see, there are two goals with this system. Number one, to increase the rate of calcium administration, and number two, improve hypocalcemia and hemostasis. From this, we hope that reducing the incidence of hypocalcemia ultimately improves patient outcomes. But so far, there hasn't been any evaluation on whether or not this is actually effective. That's where I come in. So in this project, we want to first see these calcium flashers actually achieve these goals and actually reduce hypocalcemia. To do this, I examined trauma patient charts from before and after the implementation of this system. I recorded lab values such as calcium levels, coagulation testing, patient treatments, and outcomes. And we'll later be comparing these two groups of data using descriptive and statistical analysis. I'm currently on the second step, so we're not too far along on this project. And from our results, we hope to gain insight on the current efficacy of calcium flashers, and then decide from there if we need to implement any future changes to our current system. In conclusion, this project has great potential to improve the quality of care for future trauma patients. And I really look forward to finishing our chart review and to what our next steps may be. And here's a few ideas up here in the case that our current flashers aren't very effective. Thank you for listening and for your time. I'll now be taking any questions. Yes, I am poster number 10, so come find me later. Thank you, everyone.
Okay, and next up is Nathan.
All right. Hi, everyone. My name is Nathan. It's my pleasure today to speak with you about my presentation titled Identifying Ribosomal Protein and Biogenesis Factors Involved in Virus Translation. So this has been a project that I've been helping out on in the Foster Lab this past summer. So this project is focused on looking at the relationship between viruses and ribosome translation. So viruses are very diverse, but what makes them very common is that they all require a host in order for them to propagate and replicate themselves. So generally, as a result of this, ribosomes of the host cells are often used to translate virus proteins. So in our project, we're focused on looking at two main ribosomal factors, the first of which being RPL28, which is a component of the large 60S ribosomal subunit, as well as BOP1, which is a biogenesis factor, so it's involved in producing new ribosomes, and that's what facilitates ribosomal RNA processing in cells. And our hypothesis is that due to the role that RPL28 and BOP1 already have on existing ribosome composition and biogenesis, they may also play a role in effective virus translation. And the virus infection model that we decided to use was Coxsackie virus B3 or CVB3. So to accomplish our research objectives, there were two main workflows that we implemented. The first of which was to generate knockdowns of our proteins of interest. So generally a good way to figure out what something does is to knock it down and see what happens. So we did that with RPL28 and BOP1. So we transfected an A549 cell line with siRNA of either RPL28 or BOP1, and then also did a firefly luciferase as a control. Samples were then collected, and we then verified the knockdown using either a Western blot or mass spec, and also assess the cell viability, just to make sure that exposure to the siRNA and the knockdown wasn't actively harming the cells. After that, our cells were then infected with CVB3 at an MOI of 1, and samples were then collected across various time points, and a plaque assay was then used to determine viral titer. So from our results, we can see that there is no impact to cell viability between the two treatment groups. And also from the Western blot, as you can see on the left side of your screen, cells transfected with the siRPL28 indeed had a reduced quantity of RPL28 protein. We can also observe a reduced viral titer in cells transfected with siRPL28 at the 6 hours post-infection time point. However, this is not necessarily considered statistically significant due to the p-value being slightly above the 0.05 threshold. This may very well be to the presence of outlier replicate 1. So definitely more replicates are going to be done with our RPL28 experiments. Also, most of the results shown today are for RPL28 knockdowns. BOP1 knockdowns have also been done, but they're still very much in preliminary results. So future aims are also going to be focused on delving a bit more into our BOP1 experiments. And yeah, thank you very much for listening. And I'm open to any questions or come up to me at the end as well at our poster presentation. Thank you. Yes.
Yeah, so very interesting. So we worked on consecutive virus. So there's a lot of turnover of the liposomes. So how much knockdown do you need to see some effects? What cells actually using so that is this?
Oh, so the cell line we did was A549. And so the first part of your question is how much knockdown we do, or?
Yeah, how much, you know, because it's siRNA,
Oh.
how effective is actually knockout to actually see something? Because I would guess if you knock this gene down too much, you get the result. I don't know.
Yeah, I think, yeah, so across these three replicates, we can see like comparing like the treatment group versus the control group, that there is this relatively fainter RPL28 protein quantity for the knockdown cells. In terms of how much knockdown we do, I don't know, we just followed a protocol, I guess. But yeah, I'm not sure exactly what it would look like if we scaled up or down, but yeah, that could definitely be something that could be looked at in the future.
Okay, next is Quinese.
Hi everyone, my name is Puneet and I was a summer student here at Dr. Kamei's lab. And to start off with, what are biomedical devices? So a biomedical device is an instrument or device that is used to treat, diagnose, or prevent any abnormal physical conditions. And the use of these devices have increased rapidly over the past decade, meeting the needs particularly of an aging population. However, the presence of these biomaterials in the body leads to an immediate thromboinflammatory response from the host. And this is not only damage to the device and loss of its function, but also harm to the host. So to prevent thromboinflammation at the biomaterial surface, we have two approaches. The systemic approach is the administration of an anticoagulant and anti-inflammatory drug, such as receiving an intravenous. However, the problem is they increase the risk of bleeding and have other side effects. And the second approach is the local approach, which is the development of protective coatings for blood-exposed surfaces. However, most developed coatings have anticoagulant properties and they do not block inflammation. So my project focuses on immobilizing a naturally occurring protein called thrombomodulin, specifically its lectin-like domain, to a biomaterial surface to prevent inflammation by reducing leukocyte adhesion and complement activation. And the plan for my project was, number one, express this protein in the mammalian cells. Number two, check for its functionality. And number three, conjugate it onto a coating. Here on the left, I'm showing you the results of the purification of thrombomodulin lectin-like domain in the mammalian cells by affinity chromatography. And as you can see, there is a strong signal at the expected size, proving that the protein that I found was actually thrombomodulin. And now that we have expressed and purified this protein, it was time to see whether it was functional or not. So through several functional analyses, I find out that thrombomodulin lectin-like domain decreases the activation levels of the complement pathways, specifically in the classical and lectin pathways in a dose-dependent manner. And in summary, I expressed and purified thrombomodulin lectin-like domain and discovered that it is functional. And for my future steps, I will further assess its functionality by a leukocyte adhesion and upscale its expression, and finally add it to a surface that is exposed to blood. And my final goal is to create a safe and anti-inflammatory coating for biomedical devices and prevent what is happening in the photo. Thank you so much for listening.
Anyone have any questions? What's your poster number?
Yeah, it's number 9.
Okay, so people can have questions with your poster. Okay, now we're going to hear about the role of the microtubule.
Hi, everyone. My name is Kwon, and I have been working in the Kim lab over the summer. And I've been working on my project involving investigating the role of microtubule in platelet function. So platelets are small cells in the blood that originate from the bone marrow, and these circulate the bloodstream, and then they can be exposed to various agonists, including thrombin, leading to the activation of platelets and result in the blood clot formation. So platelets have 3 main types of granules: the alpha granules, the dense granules, and the lysosomes. And upon activation, these granules will be secreted, also releasing certain markers such as the p-selectin as well as ATP, which we can measure as the extent of platelet activation. So it is known that the platelet activation can be regulated by the cytoskeleton, which has 2 main components, the actin and the microtubule. It has been shown that the actin can regulate the platelet shape change, as you can see in the top right figure. And our lab has also shown that the actin can regulate the granule secretion, as the data is shown by provided by Dr. Manoj Paul. So in this experiment, he inhibit or promote the actin polymerization process. And he's shown that the inhibition of the actin polymerization in platelets actually promotes the granule secretion in platelets. Microtubule, on the other hand, has also been shown to regulate granule traffic in other cells type. However, there's no evidence of microtubules involved in platelet granule secretion. So my goal of this project is to investigate if microtubules has a role to play in this platelet secretion. So my approach used a certain drug called colchicine, and this will inhibit the microtubule polymerization process. My study used mice blood. So I collect the mice blood, isolate for platelets, and then treatment with colchicine. And then I activate the platelets with thrombin or as a negative control, just treatment with buffer. And then after that, I compare the expression of P-selectin as well as ATP secretion in these platelets. So my result shows that the colchicine does not have a significant impact on the role of platelets in the resting state. When you compare the colchicine treatment to the resting condition, there's no change in P-selectin and ATP secretion. We also activate the platelets with thrombin after the treatment with colchicine, and there's no significant change to the P-selectin expression as well as ATP secretion, indicating that colchicine does not have a role to play, does not have an impact in platelet granule secretion. So in conclusion, the microtubules is not essential for granule secretion. And in my future direction, I hope to investigate if the colchicine actually has been properly taken up by the platelets. Thank you, and I'll take any questions.
Questions?
My poster number is 6, if you have any questions.
Thank you. Okay, Ralph, where are you?
Hi, my name is Ralph, and today I'm going to talk about my research project. So a little bit of background info. Canada right now is facing a blood shortage problem, partly due to the pandemic. There are a lot less donors available, so a lot less blood is being donated overall. And so we want to reduce the amount of blood wastage occurring whenever we can. Right now at our hospitals, if a blood unit is taken out of inventory, it's often marked with a pen to indicate that it's been checked. But if it ends up being unused, then it gets thrown away and discarded. And also sometimes if a blood unit gets taken out and put into an infectious ward, there's no standard protocol on how to actually disinfect the blood bags, so those also get discarded. So for my research question, I want to know, do pen markings and surface disinfectants applied on the bag surface affect the quality of red blood cell concentrates? So for my study design, it's really simple. I take 4 blood bags from 4 different donors, I pull it together and split them back again to the same bags so I can make a more homogeneous mixture. And I either mark it with a pen or I clean it with the disinfectant according to its contact time. For the assays, I sample the blood bags 24 hours after application and on day 42 because day 42 after initial collection, because that's the maximum shelf life of an RCC unit. And I test for hemolysis, potassium, morphology, deformability, and RBC count. And for my results, so the first set of bars indicate the first time points, the second set is the second time points. And basically for the RBC count, hemolysis, potassium, morphology, there were no statistically significant differences between the control bags and the different study arms. I didn't show all the graphs because I couldn't fit them all here. Oops. But basically for the disinfectants, the results were essentially the same. And so conclusion and future direction, what did we learn? Pen markings and decontaminants do not decrease red blood cell quality. And now we know it's safe to use on blood bags and don't have to be discarded and thrown away. And hopefully with this data, we can change current protocols at our hospitals to reduce the amount of blood wastage occurring. Thank you for listening. Does anyone have any questions?
Questions for Ralph? So do you have any idea what the wastage rates are for these units of red cells?
I could not find for info on red cells. I can only find it for platelets. Yeah, so I can't say how much it is.
So we have we throw away almost a third of the platelets.
Yeah, I think so. Yeah, we throw away a lot of blood. So if you guys are able to donate blood, please donate. Yeah. We are in need of blood.
Yeah, we're down about 31,000 donors since the pandemic, and so we're desperately trying to replace those people.
If you have any more questions, I'm in poster number 3.
Okay, Sophia.
All right. Good afternoon. My name is Sophia Levy, and I'd like to start off today by having you all imagine two women running a marathon. So now imagine that one of the two women is wearing a weighted backpack. It isn't so hard to see that this added burden is likely to slow her down and may even cut her race short, while the other woman is able to run much more freely. So this concept of an added burden is at the center of my project. However, instead of weighted backpacks and marathons, I chose to focus on how lifelong viral infections can impact the healthy aging of women living with HIV. So one common misconception even today is who the average person living with HIV is. In reality, over 50% of people living with HIV globally are women. And strikingly, in Canada, women living with HIV have a 5 to 10 year shorter life expectancy than men living with HIV and HIV negative women. So why is this the case? One hypothesis is that when someone acquires multiple lifelong viruses, this can cause a burden on their immune system, resulting in organ damage and leading to a shorter life expectancy. So my project aims to determine the prevalence of 5 lifelong viruses in women living with and without HIV, and to calculate all-cause mortality in both groups. So this project involves 126 women living with HIV and 164 HIV negative controls from the BC Karma-Chiwos collaboration, or BCC3 study. This is a cohort study which uses a holistic approach to go far beyond just biological samples to learn more about the social, clinical, and cellular complexities which impact women's healthy aging. To address my first aim, I determined the prevalence of herpes simplex viruses 1 and 2, varicella zoster, and hepatitis B and C in both groups. And in the analysis, women living with HIV were more likely to have herpes simplex 2, hepatitis C and B, but not varicella zoster or herpes simplex 1. Next, I looked at a clinically relevant outcome, the VAX index, which estimates 5-year all-cause mortality based on some commonly used laboratory tests. On average, women living with HIV had a higher risk compared to controls. So this index allows us to examine the data even further, as you can see on this graph. The blue line there shows the optimized baseline risk with respect to age group. And we can see that even though the risk for all women is at or above the baseline, the difference between the women living with HIV in purple and the controls in pink appears the most prominent after the age of 40 and persists with age. So to summarize, this project has shown that women living with HIV had a higher prevalence of 3 out of the 5 viruses studied and had a greater median risk of 5-year all-cause mortality. Moving forward, we'll investigate the relationship between these 2 parameters and other factors which influence aging, with the ultimate goal of finding actionable ways to lighten the metaphorical backpacks of women living with HIV. Thank you all very much.
Yeah, you've got the difference between men and women's survival. Do you have any explanation? Are women with HIV a different socioeconomic group than the men, or what? Are you looking at that?
We're focused on women living with HIV, so not in our study. We're not really looking at the difference between the socioeconomic factors between men and women, but we are definitely collecting a lot of data on the socioeconomic factors of the participants, the female participants in our study. But that's definitely something that would be interesting and to look at in the future.
Very interesting. You showed us mortality at the time earlier, but actually do the age faster. How do you really define age?
Yeah, so some things that we're looking at on the cellular level is we're looking at telomere length, because as we get older and the cells divide, the telomeres get shorter. And we're also looking at mutations in the mitochondrial DNA, because that also can be an indicator of aging. So those are some of the cellular tests that we're looking at with regards to aging. Any other questions?
What's your poster number?
Number 7.
Thank you. Okay, now we're having a change of subject.
All right. Hello, everyone. My name is Tian. I'm working on the Hancock Lab. with Dr. Haney for the summer, and my project is about the synergistic effects of anti-biofilm peptides and conventional antibiotics against bacterial biofilm. So let's get into what a biofilm is. Biofilm is formed when a cluster of bacteria adhere to a surface and at the same time surround themselves with these polymeric substances that protect themselves from the attack of drugs like antibiotics, hence the term adaptive resistance. So we probably all know that biofilm-associated infections seen in cystic fibrosis patients or chronic wounds is very difficult to treat since antibiotics don't work on them anymore. Recently, however, novel peptides have shown a lot of activities in eradicating these biofilm and offer a potential for biofilm-associated infection treatments. Hence my research goal for the summer, to explore the synergy combinations between the peptides and conventional antibiotics. After selecting some clinically relevant antibiotics, I performed checkerboard assay, as you could see the microtiter plate to the left, sorry, to the right. And then I use FIC index, which is fractional inhibitory concentration index, to see the interaction between the two drugs, whether they are synergistic or antagonistic, meaning working against each other. So I want your attention to shift to the table lower to the right, is how we would expect synergy happen in a microtiter plate, where you can see the gradient ranging from bolus to litus. Litus meaning there's no biofilm left over after the treatments. And the value bolded in green, dark green, is show synergy, as the FIC index values is calculated to be 0.4, which is smaller than 0.5. So let's look at our result. The results show that aminoglycoside, the antibiotic class, is shown to eradicate Staphylococcus aureus as it synergizes with biofilms. Synergizes with the peptides. For the Pseudomonas, it's only streptomycin. Promisingly, antimicrobial metal ions also synergize with peptides to eradicate the bacterial biofilm. So what does this mean? This means that anti-biofilm peptides can synergize with peptides to eradicate bacterial biofilms, and this could offer a new treatment strategy for biofilm-associated infections. And with future direction, we want to validate synergy in a more sophisticated synergy models like in vivo, and also want to confirm the resistant development of these combinations. Thank you so much, and I now take any questions you may have.
So one of the big problems with blood component production is that we get biofilm formation in platelet units because they're stored at room temperature. And so do you think that any of these compounds would be useful in that context?
I think definitely could be, because anti-biofilm peptides have shown to inhibit as well as eradicate biofilm. So even if we add in the synergy combinations before in the blood, this could also inhibit the formation of biofilm and also even eradicate biofilm potentially. Any other questions? Number 5.
Okay.
Good afternoon, everyone. My name is Waris, and I am a student from Kisakadathu Lab. And this past summer, I've been very lucky to work on the project, developing universal blood using novel enzymes to modify the RBC surface. So what is universal blood? So universal blood is the idea that we can make donor RBCs, which are transfusable without the need for blood typing. And why do we need universal blood? So first reason would be to meet the ever increasing need for blood supply. And the other one would be to circumvent the need for blood matching, especially in cases where there's a limited time. So just to give a little bit of background, let's look at the ABO blood group. So terminal sugars of
long carbohydrate chains. They encode and characterize A and B antigens as shown here. And if there's a mismatch of the ABO antigens, it could cause an immune reaction, which would lead to hemolytic transfusion reactions. And if the person does not have either of those antigens, they would be said to have O-type blood, which means that they could donate RBCs to recipients without recipients of the ABO blood group. So just to look at that, in our lab, we use novel enzymes to cleave off the A and the B antigen. So we use an enzyme pair to cleave off the A antigen, and similarly for the B antigen, we can use a B antigen cleaving enzyme, which would result in O-type blood. But this does not solve the problem for Rh antigens, which are transmembrane proteins on the RBC membrane. So in order to solve that problem, we use a different enzyme that creates an immunocamouflage effect. The RBC has a unique glycophilic structure or sugar coating, which also includes sialic acids. And we use this enzyme that can directly polymerize polysialic acid on the sialic acid already present on the RBC membrane, which leads to subsequent evasion from antibody detection, as seen here. So this can have potential use in transfusion therapy, and we propose that it could help prevent adverse reactions for unintentional mismatch of blood types. Thank you for listening, and if you have any questions. Poster number 11.
Do you anticipate that there might be cross-reactivity of these enzymes for antibodies with any other blood components, or does that work?
I haven't really thought about that, sure. But when we directly work on whole RBCs, just packed RBCs. So yeah, so that's the future.
Okay, I think that that wraps up our student presentations for this morning. So we do have a People's Choice Award. So I would encourage everybody to go to this link and submit your vote by 4:30, and then we will have an announcement after the fact. And I'd like to ask all of the students who just presented to come to the front of the room so we can take a picture of you. Okay, the next thing we'd like to do is to award the Neil Mackenzie Mentorship Award. And I'd just like to say a few things about Neil. Neil was a postdoctoral fellow at the UBC Centre for Blood Research who tragically passed away in a climbing accident at Joffrey Peak on Sunday, January 11, 2015. Neil was a wonderfully unique person. He passionately embraced life through his explorations in science and the outdoors, infecting others with his enthusiasm, anxious to learn, and always happy to teach and encourage others. Neil completed his first postdoctoral fellowship in his home country of Scotland. Although he flourished in that position, his love of the mountains led him to consider becoming a full-time climbing instructor in Canada. However, when the opportunity came to take on another postdoc at UBC Centre for Blood Research, Neil decided to stay in academia and pursue outdoor activities as a leisure activity. At the time of the tragic accident, Neil was well on his way to making major strides in Dieter Brahm's lab toward understanding some of the mechanisms underlying cardiovascular disease. He embodied all the definitions of a mentor, in and out of the lab, a consummate learner and teacher, enthusiastically engaging those around him with his quiet charm. One of the most active members of the Varsity Outdoor Club, Neil could be found climbing practically every weekend. He was known to support any beginner and was happy to show them the ropes. Bad pun. He had a unique talent to connect with people thanks to his disarming and self-deprecating sense of humor that put people at ease in any kind of situation. When Neil wasn't climbing, skiing, snowboarding, sailing, biking, canyoneering, hanging out at the beach, or doing just about any other outdoor activity one can think of, Neil was an easygoing, laid-back guy who loved to be around people. As a proud Scotsman, he loved whiskey and, of course, haggis. He was an avid music fan, in particular of hip hop and bluegrass. With all of these talents and interests, his housemates describe him still as a very modest person with a bright and bubbly personality. And I'd like to announce that our 2022 winner for the Neil Mackenzie Mentorship Prize is Dr. Samantha Grist. Who I'm hoping is here somewhere. Yep, there you are. Okay, great. So come on down here. We have a little gift for you. And you get to say a few things. Thank you. Okay.
Wow. This is really such an honor, and I'm immensely grateful to those who nominated me, as well as to the CBR for facilitating this award. I honestly cannot overstate how much this award means to me. I really see mentorship as the most important part of my work, because we can have so much more impact by working together as a team and helping each other than we can ever hope to have individually. And I also really love working with and learning from each and every student. So being recognized for my mentorship is, for me, the biggest honor, and I'm so grateful and so humbled. I was asked to say a few words about my mentorship philosophy, and I think that the driving philosophy for me is really just continuous, lifelong learning and striving to do better. There are 3 key values that I center in my mentorship. First, I try to tune my mentorship style by listening and learning from each and every student how I can better support them. Every one of us is different, and I hope to learn and use effective strategies to serve the unique needs of every student and create opportunities to help them achieve their own unique goals. Just like in my science, I try to keep an open mind and learn from the experts, learn from the peer-reviewed literature, and collect data in the form of feedback from each student to learn to do better. Second, I try to create safe, inclusive, and supportive environments and prioritize documentation and onboarding and training resources to try to help set students up for success. I strive to create a culture that asks each other the hard questions and supports each other in doing really rigorous science, and also cultivates curiosity and joy in our science and recognizes and celebrates all successes. Finally, and most importantly, I think it's critical to understand that we are all human. We will all have bad days and deliverables that are not our best, and we will all make mistakes and things will go wrong. And I want to do what I can to listen and support and help the folks on my team during those times, and where possible, learn from these experiences as a team to solve problems and improve our documentation and training to help to make it easier for the next students. Now, on a personal note, I'm incredibly grateful to my own mentors, without whom I would not be here today. It was mentorship from Professor Karen Kavanagh in SFU physics during my very first co-op term that made me realize that I could be a scientist and an engineer. And it really stopped me from dropping out of my program at that time. It was mentorship from my undergraduate thesis supervisor, Professor Bonnie Gray in SFU engineering, that guided me through my thesis and my first international conference presentations, giving me the confidence and the inspiration to pursue graduate school. It was mentorship from my PhD supervisors, Professor Karen Chung and Professor Lucas Krastowski here at UBC, that helped me to overcome imposter syndrome, to solve some really fascinating research problems, begin to mentor other students, and complete my PhD. And it was mentorship from Professor Amy Herr at UC Berkeley Bioengineering, where I did my first postdoc, and my current supervisors, Professor Karen Chung, Professor Sudeep Shaker, and Professor Lucas Krastowski, that supports me and grows my confidence, gives me endless opportunities to grow and learn, and sets an excellent example of diverse leadership styles for me to learn from. And this is only my formal mentors. Of course, there are countless informal mentors and colleagues to whom I'll always be grateful. And it was through my own mentorship and learning from each student with whom I've had the privilege of working that motivates me and helps me to be the best mentor I can. And I'm so grateful to every one of those students. Mentorship has had such a transformative impact on my own growth, and I'm grateful every day for the opportunity to try to give back some of what my mentors have given me. Sorry. Because of this, and because of how heavily I value helping to support the team, I can honestly say that this is the most meaningful recognition that I've ever received. So thank you so much. It really means the world to me, and it inspires me to continue to work, learn, and grow to be the best mentor that I possibly can. Thank you.
Okay, we're about half an hour ahead of where we're supposed to be, so maybe we want to take a break. That's okay with everybody. So we'll come back at 2:30 for our keynote talk. Okay, I think we could get started again, and we'll give Dr. Blakney a few extra minutes to give her presentation. And I'd just like to do a formal introduction where I'm very pleased that Anna's here with us. And she's an assistant professor in the Michael Smith Laboratories and the School of Biomedical Engineering at UBC. She received her Bachelor of Science in Chemical and Biological Engineering from the University of Colorado at Boulder, which must mean she's a skier, and her PhD in bioengineering from the University of Washington. She completed a postdoctoral fellowship at Imperial College London on the development of molecular and biomaterial engineering strategies for delivery of self-amplifying RNA. Her lab uses bioengineering, molecular biology, and immunology approaches to develop the next generation of RNA vaccines and therapies. So obviously in these times of COVID, she's very appropriate to be giving us a talk. So, Anna.
All right. Can everybody hear me okay? Great. Thanks very much for the introduction, and I'm really pleased to be here today. I got some of the student presentations, and it's always so invigorating to see all of the different science that's happening in the Center for Blood Research. So I'm really honored to be here today. So today I'll be talking about some work from my postdoc, as well as what we do in my lab here at UBC, working on next generation RNA vaccines and therapies. So just to give you an outline of my presentation today, I'll talk a little bit about what we do in the Blakney lab here at UBC. For those of you who haven't heard of self-amplifying RNA before, I'll give you a little introduction to that. I'll also talk about my experience with working on the development of the Imperial College COVID-19 vaccine that finished its phase 1/2 combined trial last year, as well as where I think we're going with the future of RNA medicine. So just to give you a little intro to my lab, it's been a really exciting time to be in the field. I used to have to give, the first half of my talk, first 30 minutes, just explaining what RNA vaccines were and really trying to convince people that they could potentially work one day. So I like to say now the plane is really off the ground. So it's a really exciting time to be in the field and really think about where are we going next with this technology now that we've seen what an impact it can make on the COVID-19 pandemic. So my lab specifically is really interested in looking at RNA molecular engineering. So how can we design better RNA? My background is really more in biomaterials. So we're always looking to design new formulations that get more RNA to the cells and tissue where it needs to go, as well as thinking about how do we make better vaccines and use RNA for other applications. So some of the things we're working on now are other vaccine applications that have unmet clinical need, like chlamydia. We're seeking to understand gain a better understanding of the immune response to RNA vaccines. There's still a lot we don't understand about these vaccines, as well as using RNA to express monoclonal antibodies, which could be used for treating cancer or preventing infectious diseases.
So one thing I really want to highlight, and kind of one of the priorities in the field, has really emerged from all of the amazing clinical data that we have now from the COVID-19 mRNA vaccines. So this is some data that was from Moderna's initial dose finding clinical trial. And there's a lot of data here, but I'll walk you through it. So in this trial, they looked at 3 different doses of RNA, so 25, 100, and 250 micrograms. And these are all the side effects that they observed in patients that got these 3 different doses of RNA. So the gray is mild, the blue is moderate, and the yellow is severe. And what I think this data conveys pretty obviously is that as you increase the dose of RNA, you see an increase in the number of the severe side effects. So what we know now is that the dose of RNA is directly proportional to the frequency of severe side effects. So one of the biggest challenges in the field right now is really minimizing the dose of RNA that's required for the use of mRNA vaccines, because as you can imagine, people were willing to undergo these vaccines and these side effects in the context of a pandemic, but maybe much less willing to do so for an annual flu vaccine or other vaccines, as well as other applications, like if you're going to get a treatment or a therapeutic. So this is one of the things that we're really thinking about now is how do we minimize the dose of RNA such that we can make better vaccines and use this for other applications. So to give you a little introduction to self-amplifying RNA and how this kind of helps address this challenge, I'll walk you through kind of the structural and practical difference between saRNA and mRNA. So at the top, most of you are probably very familiar with conventional messenger RNA. So there's a few key components here, including a 5' cap, a 3' poly A tail, and then an untranslated region at the 5' and 3' end. And then for a vaccine, we have our gene of interest here, which is the antigen. So self-amplifying RNA is structurally very similar to messenger RNA. So it again has a 5' cap, a 3' poly A tail, a 5' and 3' untranslated region, but it's derived from an alpha virus. And so you'll notice here that it has these 4 non-structural proteins, or NSPs, and these NSPs make up a replicase. And I'll get into a second in how this affects the RNA intracellularly. But how we attune this is that normally in the viral genome, you would have your structural proteins here. And instead, we take out those structural proteins so it can't produce new viral particles, and we instead put in the antigen. So it's still a single-stranded linear RNA construct, but it's much larger than messenger RNA. So how this varies practically is once it gets into a cell, for messenger RNA, once we get 1 copy of mRNA into a cell, it engages with the ribosome, and then you get translation of your antigen. saRNA starts out very similarly. So once we have 1 copy of the saRNA, once it gets into a cell, it again engages with the ribosome. You do get some translation of your antigen from this initial engagement, but you also get translation of this replicase enzyme that comes from these non-structural proteins. So the replicase then goes back and engages with this original strand of saRNA and makes thousands of exact copies of it. So because of this, you get much more antigen translated from the same initial amount of RNA. So usually this means that we can use about 100 times lower dose of saRNA compared to messenger RNA. So when we think about this in the context of the COVID vaccines, for the Pfizer and BioNTech vaccine, it's a dose of 30 micrograms and Moderna is 100 micrograms. So that means, in the context of a vaccine, we could use 100 times lower doses, which should help to mitigate some of those side effects that we see. One of the biggest challenges in the field of nucleic acid vaccines is delivery. So these are large negatively charged molecules, and so they're very challenging to get into cells. So this is also some of the work that we've done in my lab. One thing I wanted to talk about today that's a really exciting aspect of what we're working on is that what's really amazing is that we, in the field of saRNA, people have really only used 3 specific viruses to make saRNA backbones. So even though we have this landscape of so many different viruses, including all of these positive stranded, single-stranded RNA viruses, to date, we've only used 1 class of these, which include alpha viruses. So the 3 that people have used, Venezuelan equine encephalitis virus, which is the most common, that's kind of the one that everybody uses.
Sinbis virus, and some leaky forest virus. So we have some collaborations now with Nozomi Yachi and Eric Jan here at UBC to develop new saRNA vectors, because there's a whole world of viruses out there, and we think that some of these applications will be better for vaccines, will translate better in certain cell types, so will help us control the cellular tropism, as well as maybe have different expression profiles so we can use these for other applications beyond vaccines. So we're also working on a lot of delivery vehicles. So for those of you who aren't familiar with the nanoparticle delivery technology, the paradigm in the field is that you take your solution of negatively charged saRNA and complex it with some positively charged delivery vehicle. So most commonly, this is done through a microfluidic device using a chip. And then at the end, you get this nanoparticle where the RNA is encapsulated on the inside of the particle. So in the field, people for saRNA specifically have done this using 3 different delivery vehicles. So polymeric nanoparticles, some of which we use in my lab, lipid nanoparticles, which we also use, which were really developed by Peter Cullis here in the biochemistry and molecular biology department, and are also used in both of the approved mRNA vaccines, and nano emulsions. So one of the questions that we're really interested in looking into on the delivery vehicle side, I always think back to this schematic that was published by Norbert Party in 2018. And Norbert works really closely with Drew Wiseman at University of Pennsylvania, who obviously discovered the modified nucleotides used in mRNA in collaboration with Katsu Kariko. So they put out this really fabulous review in 2018. And what they're really detailing in the schematic is that we know a lot of ways that RNA is sensed intracellularly, right? Because we've studied this in the context of viruses for a long time. So we know we have these endosomal RNA sensing mechanisms like TLR3, 7, and 8. We have these cytosolic RNA sensing mechanisms, some common ones like MDA5 and RIG-I. But what always stood out to me about this schematic is that there's this big question mark about carrier sensing. So we know that the cells must be sensing these nanoparticles. We just don't know how they're sensing the nanoparticles. But there's some preliminary evidence now that this actually plays a big role in the immunogenicity that you see from the vaccine. And you really need to kind of tailor this to be able to use it for other applications beyond the vaccine. So this is something that we're working to understand as well. So one of the things I was working on during my postdoc was an saRNA vaccine. We were actually planning on doing clinical trials in 2020 anyways. And then when the pandemic hit, we pivoted and made a COVID vaccine instead of the vaccine that we were planning to take into clinical trials, which was against Marburg and rabies viruses. So just to walk you through the process of that, so we were an academic team at Imperial College. You've probably seen a fair amount of this now, but I'll walk you through how exactly you make an RNA vaccine against a new pathogen and just what's really amazing about this technology and the timelines that you can accomplish this on. So in order to make our saRNA vaccine, we took the spike antigen from the SARS-CoV-2 virus here. We encoded the pre-fusion stabilized spike antigen in our saRNA. We formulated it into lipid nanoparticles, and this was actually done in collaboration with Acuitas, which is based here in Vancouver, and then started our preclinical animal studies. And what's really a game changer for RNA vaccines is it's so much quicker to get into the clinic with these vaccines compared to traditional types of vaccines. So I'll walk you through the timeline for our team. So on the 10th of January 2020, the circulating strain was sequenced and made available to the public. We accessed that sequence on the 20th of January. I coincidentally flew to Vancouver the next day on the 21st of January to interview for my position here at MSL. So as you can imagine, it was a very busy time. We ordered the DNA oligos on the 22nd of January. We assembled our new plasmid on the 28th of January. We confirmed that we were getting the spike antigen expression from our saRNA in vitro on the 12th of February. And so we started our immunogenicity studies in mice the next day on the 13th of February. Because this was a first in human clinical trial, we had to do a rat toxicology study before going into a human clinical trial. So we started that on the 30th of March. We submitted our paper on our preclinical findings on the 22nd of April, and then started our clinical trials on the 19th of June. So even as an academic unit, we were able to go from designing a brand new RNA vaccine to testing it in a phase 1/2 combined clinical trial
within 6 months. So this is a really unprecedented rate of vaccine development, but it doesn't mean we were able to skip any of the safety steps or anything like that. It's just making these is so much more modular than previous vaccines. And we did this in about 6 months, but Moderna reportedly did it in just 66 days. So this is the only data that I'll show you from this, but I just really want to highlight what low doses that we're able to use in these vaccines. So there's a lot of different categories here, but I'll walk you through what all the groups are. So this was some of our preclinical data in a mouse model. And we used a few different groups as positive and negative controls. So at the time, there was really no standard for an mRNA vaccine or formulation to compare against. And so we used electroporated DNA in our lab as our positive control, because this gave us very reliable antibody titers. We compared it to a negative control against rabies to make sure that we were seeing a specific immune response. And then we tested 4 different doses of saRNA encapsulated in our lipid nanoparticles. So 10, 1, 0.1, and 0.01 micrograms. And this was very early on in the pandemic, but we were able to get serum from recovered COVID-19 patients from the local hospital. And so we were able to compare our antibody titers compared to those that had just recovered from natural infection. So on the y-axis, we have the SARS-CoV-2 specific IgG as measured by ELISA. These mice were primed at 0 and then boosted at 4 weeks. And then we measured the antibody titers at 2, 4, and 6 weeks. So you can see here with our DNA, we got a really good antibody titer, just what we were expecting of about 10 to the 5th nanograms per mil, nothing from our negative control. And you can see with our highest dose of saRNA, which was an equivalent 10 microgram dose to the DNA, we see almost 10 to the 6 nanograms per mil for the antibodies. There's a really nice dose response curve here, even down to our lowest dose of 0.01 micrograms. And you can see that even at this lowest dose, we were still seeing a higher antibody titer than in the patients that had recovered from COVID-19. So people always ask me, where is the ICL vaccine now? So we finished our phase 1 and 2 clinical trial in January of 2021, just as I was starting here at UBC. At the time, there were already approved vaccines in the UK. So the AstraZeneca vaccines and both RNA vaccines were approved and starting to be distributed there. And so the government didn't want to invest another 130 million pounds to do a phase 3 clinical trial, which makes sense. They wanted to allocate the resources elsewhere. So the team decided to pivot to targeting mutations for COVID, as well as looking at booster doses. Because of this, I am co-founder of a company that's called VaxEquity that is developing this saRNA vaccine platform. And what was really exciting is that last year we announced a partnership with AstraZeneca to continue developing this vaccine platform. So there's a lot of excitement in the field. And what's really exciting is that even more recently, just a few weeks ago, the first saRNA vaccine against COVID-19 was approved in India. So this is at a dose of 5 micrograms. So it's really quite invigorating to see this technology really taking off. And lots of people are excited about this now. I think every big pharma company now has an RNA branch and are really working to develop this technology. So it's been an incredible time to be in the field. So I want to get into forward thinking and where I think we're going with RNA medicine. So one of the most important aspects of this, which isn't very sexy to talk about, but the manufacturing of RNA is actually a lot easier than protein or viral vector vaccines. So this is a picture of how we manufactured the flu vaccine in 1957 in eggs. And this is actually still how we manufacture most of the flu vaccines today. And so this is a very manual labor and time intensive process. We have to decide in February each year what strains we're going to put into the flu vaccine so that's ready for distribution in October for the Northern Hemisphere. So because of this, there's a huge lag time between the flu that's circulating at that time, and you kind of have to make your best guess for what strains are going to go into the vaccine. In addition, other vaccines like protein vaccines and viral vectors require these huge bioreactors for the cells to grow and produce the protein or the viruses that then have to be purified out. And it's again, a very time and resource intensive process. So RNA, on the other hand, is a completely synthetic process. So that means we can just make it in a test tube. And what's really amazing about this is that for saRNA, 100 mil volume can make about 1 million doses. So it's so much more scalable than these old technologies in comparison. So just to put this volume into perspective, I asked the question, how many Olympic-sized swimming pools would it take to vaccinate the entire world with an mRNA vaccine? So I did this calculation for the Pfizer and BioNTech vaccine. So assuming there's 7.7 billion people in the world and initially everybody needed 2 doses, it gives us now 15.4 billion doses total required. Each dose is a volume of 0.3 milliliters. This gives us a total required volume of 4.62 million liters. Each Olympic-sized swimming pool is 2.5 million liters. So this means that we just need 2 Olympic-sized swimming pools to vaccinate the entire world. So an Olympic-sized swimming pool is a large volume, but what I think this puts into perspective is this is actually possible, right? Billions of people have now gotten RNA vaccines. And so this is one of the reasons why it was so easy to scale up and distribute these vaccines in the context of a pandemic. So one of the things that I think will really change is the manufacturing of RNA vaccines worldwide. And I think this will have a huge impact on how we can use these in medicine as well. So I wanted to just give you a kind of an anecdote from manufacturing the RNA vaccine for our clinical trial, which started with manufacturing the RNA in California. The lipids then came actually from Acutis here in Vancouver. They were shipped to a company in Austria to do the formulation, which then shipped the formulation to Italy to be put into vials, which was then shipped back to the UK to start our clinical trial. So even though we were doing this clinical trial in the UK, none of the vaccine was actually manufactured in country. So I think this will change. You know, at the time, there just wasn't a lot of large-scale manufacturing facilities for mRNA, but because you don't need this huge centralized footprint, I think we'll start to see these more regional manufacturing centers for RNA, where you can use it, you know, to produce vaccines for a pandemic. You could use it to make your annual flu vaccine, but in the same exact facility, you could use this to be making personalized cancer vaccines. So I think we're going to start to see this modular technology popping up in different places all around the world. So with that, I just have a few main takeaways that I hope you've gained from this presentation. So I think the RNA vaccines have very clearly made a big impact on the COVID-19 pandemic, but there's still many improvements that we can make to this technology. There's really a plethora of applications of RNA medicines beyond vaccines. So it's really exciting to see where people are taking this now that the technology has become so much more established. And I really think that the modular manufacturing of RNA vaccines and therapies will really enable more global access to these medicines. So with that, I'd like to thank the team of people at Imperial College and Acutis that worked on some of this data, as well as my team here at UBC. And with that, I will take any questions.
Test. Yep. Thanks, Anna. That was great. Question on the self-amplifying RNA. Do you observe or have you looked at any antigen presentation from the replicase? And if you do, is there any consequences of that?
Yeah, it's a good question, and it's definitely still something that we're exploring. So there's a few different components of this. So with the replicase, I guess we've never quantified the antibody response to that. Almost certainly because you're expressing this protein in a cell, you're going to get some sort of immune response to it, right? So just anecdotally, we've done studies where we've injected mice repeatedly 6 times with the saRNA, and we don't see any fluctuations in the amount of protein expression that we see from each of those injections. So even if we're getting, you know, an antibody response to the replicase, it's not hindering the amount of protein expression that we're seeing. But I think this is definitely something that we need to take into account and really understand and explore more. But one of the things is that although there's those 4 non-structural proteins there, we don't completely understand the function of each one. So almost surely some of them are actually like immune evasion proteins, or will have open reading frames for that. Because basically all these viruses have evolved to have these interferon inhibiting proteins in them. So we're still working to like really understand what all those proteins exactly do as well. Lipid nanoparticle or other carriers that cause. Oh, sorry. I think we have to turn the other.
So I was wondering if the the nanoparticles or the carriers are causing the side effects, or it's the RNA that's leading to the side effects?
Yeah, that's a really good and insightful question, because actually in that study, obviously with the RNA formulations, as you increase the dose of RNA, you're also increasing the dose of the lipid nanoparticles, right? So we're actually doing some studies now. It's possible to make empty lipid nanoparticles, so you can actually really study the difference between filled and empty particles and get an understanding of what's coming from the RNA and what's coming from the lipid nanoparticles. So it's probably honestly a combination of both. We understand the response to the RNA so much better, which is, really your body has evolved to have all these innate sensing mechanisms of foreign RNA because we're exposed to RNA viruses all the time. And so your body recognizes that foreign RNA, whether it's in a virus or in a vaccine, in the same way. So we know we're triggering that type 1 interferon response, which leads to those side effects, but it's also highly likely that some of that side effect is coming from the lipid nanoparticles as well.
Thank you.
Hello. Okay, I just want to say that your research is super cool. I also am wondering why do you think it took so long for RNA vaccines to kick off? Because there's so many benefits of it compared to, say, an inactivated virus vaccine or antigen vaccine. Like logistically, it's just so much easier to distribute to everyone. Why do you think that it took so long for this to become like a bigger thing?
Yeah, that's a great question. And I think, in all of the science communication and my TikTok videos, I get this question all the time, which is like, what is this new technology, right? And so I guess there's a couple of nuances to this. So people have been studying RNA in vivo as vaccines or other applications since the early 90s. So there's been decades and decades of research on it, right? So actually, right before the pandemic, really Moderna and BioNTech were the leaders in the field. They had both done clinical trials for RNA vaccines. But honestly, at that point, the technology was still super high risk. So there's this paper that Moderna published in 2017. It's a beautiful paper. I still can't believe that their lawyers approved it to let it out the door, because it's really not the most promising data. But they did this parallel study where they were testing a flu vaccine, and they tested it in mice, ferrets, non-human primates, and humans. And so the mouse data looks amazing. The ferret data was even better. The NHP data was just as good as the ferret data. And then when they tested it in humans, it was really disappointing. Like, not everybody seroconverted, and they didn't get to the correlative protection for that flu vaccine. So because that was just in 2017. So I think at that time, the field was still really understanding more about the modified nucleotides and the RNA that you need to really make the vaccine work, as well as the delivery system. So truly the lipid nanoparticles that were developed by Peter and Acuitas, as well as contributions from obviously many, many people around the world, that was really the game changer for RNA vaccines. So people were using all these other delivery systems early on that just didn't work. So it was really, just kind of incremental progress in the field to get to a point where it actually worked in humans. And so that happens just, I guess, very fortuitously right before the pandemic, such that then when the pandemic came, they'd used the best formulations that they had, and it ended up working super well for COVID.
Thank you. Do you think that those results contributed to maybe vaccine hesitancy when the pandemic hit, specifically for RNA vaccines?
Yeah, I mean, I think vaccine hesitancy stems from a lot of different causes, right? And we've known for years and years. Heidi Larson has done all this beautiful work on understanding vaccine hesitancy and where it comes from. But so from my perspective and what my experience has been is that there's just a huge gap between the scientific progress and what the public knows about, right? So people have been doing this research since the 90s, but even if you think back to January 2020, how many scientists even knew about RNA vaccines and what level they were at, right? And so even the questions that we still get today, like does RNA change, or do RNA vaccines change your DNA, and are they safe? These were the same questions that scientists were asking about a decade ago. It's just that we've had time to ask the questions and dig into the data and really understand it. So of course, I'm really not surprised at all that when we sprung that on people, hey, there's this brand new type of vaccine. Nobody's ever heard of it before, but it works amazingly well. Okay, let's all get one now, right? So I think it really is kind of a failure in the communication and education that we do as researchers. And this is not just for vaccines, right? It's applicable to basically every type of science, which is that if you want your science to impact people one day, you really need to start communicating about it as you're doing it. You can't wait until it's ready for prime time to start telling people about it.
Sorry, I've got an interesting question. Polio's on the up again because certain communities are not vaccinated. If you get polio in early childhood, it's not paralytic. You get it at sort of older ages, it can be paralytic. And that's a limitation of the attenuated vaccine that's currently being used for polio. And would you see a role for an RNA vaccine for polio to get around this problem? Because we're going to see cases of paralytic polio due to the attenuated vaccine.
Yeah, definitely. So I think, I'm obviously very biased because I'm a big fan of RNA vaccines, and I really see the potential for this technology. I think it's really important to keep in mind, RNA isn't the answer to every vaccine overnight, right? There's some things it works super well for, like we saw it work well for a viral glycoprotein, right? But it's still unclear, if we can use this for bacterial pathogens or other types of pathogens as well. So I think it's definitely worth looking into and really understanding the mechanisms of these more, so we know what applications RNA vaccines are really well suited for. But I think the advantages of being able to produce it at scale and quickly really makes it kind of a game changer for any vaccine.
How do you actually stop I was wondering if the replicates and siRNA have this problem. How do you actually stop it?
Yeah, exactly. So it's the same mechanisms by which, if you get infected by a virus, they have the same replicase. You could get infected potentially with one of these viruses, right? And so it's the exact same replicase, but over time, the rate of decay, which is really comes from your cells' different sensing and decay mechanisms, overtakes the rate of replication. So it peters off naturally. That's a question that obviously people are concerned about. And one of the things that I guess we've looked at and others have looked at as well is that you don't see this RNA passing on to new cells and then replicating in the new cell, right? So it has no way of like escaping the cell and then getting into another cell. So it really is just confined to the cells it was introduced to originally. And then, yeah, it really should have this replication profile that's pretty well defined. We don't understand all the mechanisms of how it's, detected and then broken down and kind of why that shift happens, why the decay overcomes the replication. But it's things we're really interested in understanding more.
First of all, thank you for a great talk, Professor Blakney. My question comes from the drug delivery side. I work in one of the labs I work in, we make polymer dots, albeit for a different purpose, but you presented 3 drug delivery methods, polymers, lipid nanoparticles, and emulsion. I was just wondering what your thoughts on the prospects of these other 2 drug delivery methods, or has the technology for lipid nanoparticles just sort of left them in the dust and is the way to go?
Yeah, it's a great question. So obviously the lipid nanoparticles just have like the most momentum, right? So both the approved mRNA vaccines as well as the approved siRNA drug all use lipid nanoparticles for the delivery. That being said, I don't think lipid nanoparticles are like the end all be all delivery method. I actually think like polymeric materials and emulsions also have their advantages. So to put this into perspective, one of the things, so with the lipids, lipids are actually, found in nature, and we think that your cells, have these built-in mechanisms to sense lipids specifically, right? So they would sense polymers in a different way, and this may have a very profound effect on like the downstream immunity that you see. So we've actually, I didn't present this today, but we've done some work on comparing polymeric and lipid nanoparticle formulations, and
Actually, what we see is that the polymers are much more immune silent. So the LNPs, this means the LNPs work way better as a vaccine. It's like 100 times better than the polymer, but we see a lot higher protein expression with the polymer. And so because of this, we think it has a lot to do with the immune response that you're getting to the delivery vehicle. So what I think this means is that, the lipid nanoparticles work really well for vaccines, but, we could potentially use polymeric delivery systems for other applications like protein replacement therapies where you don't want that immunogenic response to the carrier.
Thank you.
Sorry, yeah, I'll get to you next.
I was wondering on the topic of the replicase, if the replicase affects translation levels in the cells that it does inhabit.
Yeah, definitely. So we're piloting this new library of different saRNA designs that have all different replicases in them. And even from our initial data, we see huge differences in the replication rates and the protein expression that we see. So almost for sure that replicase enzyme and the kinetics of it totally affect the protein expression that you're seeing.
I have another question. So from my previous knowledge, I believe that immune cells, they normally react to extracellular antigens, maybe floating around your blood or in your tissues. But then these antigens from the mRNA, they're made intracellularly. So I'm wondering, is there a way for these antigens to get outside of the cell, or is there some way to adapt intracellular immunity? I'm not too sure.
Yeah, good question. So there's really kind of two different aspects to this. So with the antigen design, you can actually add a transmembrane protein or secretion signal to that protein, such that if you need something anchored in the membrane, like you might for HIV or other proteins where the structure of it is really important, or you can have it be a secreted protein just by adding that secretion sequence to it. So you have some flexibility there in your antigen design, but that actually gets to kind of a more interesting layer in the field of RNA vaccines, which is we actually don't really know, it hasn't been defined yet, what are the target cells for an RNA vaccine. So they get injected intramuscularly, but actually your immune response really develops in your lymph node. And so we don't really know if you need to have a high amount of antigen expression in the muscle or in the lymph node. And so we're starting to understand how the delivery vehicle affects where the RNA goes, what cells it's expressing, and then what cells are actually processing that protein to make your immune response.
Hi, Dr. Blakney. I have a question just in terms of when you design the mRNA and get into clinical trials within 6 months. That's it's really fast. So how do you deal with experimental designing and also planning and also dealing with troubleshooting if there was any?
Yeah, it's a good question. I think I've blacked out part of that experience just from how hectic it was. It was really all hands on deck. So the lab that I worked in, obviously a lot of us did preclinical work, but then about half the lab worked on the clinical trial. And so we really had to work together and with our team that helped with the regulators, because there's many moving parts, right? It's not just, getting the preclinical work done and making sure it's safe and coordinating everything for those studies, but it's also preparing your regulatory package to make sure that, all the study that you've done prior to going into humans, you've done everything, checked all those boxes. So yeah, it's a huge team effort getting all of that done. And it's very multifaceted, right? You really, another actually huge challenge, as I talked about, was actually manufacturing the vaccine. So because we had to do this in so many places, and RNA is very time and temperature sensitive, so you can't leave it just sitting at room temperature in customs waiting to get shipped somewhere else. And so there was a huge amount of teamwork that really had to happen to make our vaccine happen. So imagine that too for the big companies like Pfizer and BioNTech and Moderna. They were doing that really worldwide to make sure that they could manufacture this. All these different companies, even sourcing the raw materials was a huge challenge in the pandemic. And so it's really amazing to see. I think that was one of the most reassuring things about science during the pandemic, was just seeing how many people kind of went all into working on something together, and then how quickly these vaccines were able to get approved because everybody was focused on the same problem and really only that problem, right? Great question.
I have a question for you. Mm-hmm. So where do you see, like this virus, the SARS-CoV-2 virus is mutating like crazy, and where do you see these mutants? You know, kind of how are we going to deal with those?
Yeah, it's a really great question, and I would say like we're learning more and more every day, right, about how the virus is mutating, but also the immune response that we're getting from the vaccine. So I think one of the things that, again, I didn't talk about today, but I think is a huge priority in the field is really the duration of immunity, right? So we see, you know, we pretty well understand now the antibody titers after you get a vaccine or a booster, they go up and then they come down. So we're not really making a very good memory cell response there, which is what that indicates, right? And so we don't really understand why the RNA vaccines aren't doing that yet. You know, maybe we're just not getting to the right cell populations, or we're not expressing the antigen for long enough. And so I think we're working more to understand that. I think the kind of one topic that's like really understated in the media now is actually the T cell response, which I think is probably much more important than anybody is acknowledging in this, which is that your cell, like we all focus on the antibody mediated immunity for the vaccine, right? It's like, what are your antibody titers at and how long does that last? But actually the cellular immunity is a really important aspect of controlling these components. It's just that it's really difficult to measure, right? Like we're not taking samples from everybody that's got, you know, you can go get an antibody response, but you can't go get a test to see what your cellular response is like now. So I think just really understanding that duration of immunity and more about the immunity will then help us to understand, okay, why aren't we seeing like more longer lived responses from the RNA vaccines?
Hi. So obviously RNA vaccines have been really successful worldwide. I was wondering if you think it's worth researching whether DNA vaccine could actually be better than RNA vaccines, or do you think at this point it's just better to stick with RNA vaccine technology and see where we can go from there?
Yeah, so I actually the lab that I worked in as a postdoc was historically had done much more development with DNA vaccines, and there are actually approved DNA vaccines against COVID-19 now, also in India. The downside of DNA vaccines is that the delivery is even more challenging than for RNA vaccines, right? Because you don't just have to get it into the cell, you have to get it into the nucleus. So there's two membranes that you have to cross. So to date, the delivery for DNA, people have really only successfully done that with two different approaches. So electroporation, or it's like a jet injection system. So it's either like air that is like forces holes in your cell membranes to get the DNA in, or an electric pulse that opens up the membranes momentarily. And actually the lab where I did my postdoc had done clinical trials with electroporated DNA. It's a huge logistical challenge doing that. One, people hate needles to begin with, right? But then you have to tell them, actually, now we're going to give you an electric pulse right where we injected the needle. And it's painful, like it's only momentarily painful, right? But people aren't the biggest fan of that. But also, if you think about distributing vaccines on a large scale, not only do you have to have a needle and the vaccine, but you also have to have a very specific device, as well as people trained on that device to administer the vaccine. So I think just because of that, unless the delivery for DNA vaccines gets to the point where you can just inject it with a needle like you can the RNA vaccines, which is totally possible, but we just don't know how to do that very efficiently yet. I think RNA just has that slight advantage because of that.
You mentioned that the lipid nanoparticles, or the carrier particles for the RNA when making the vaccines, are made with microfluidics. So how can that be done in a large scale, in, for example, in a biopharmaceutical like plant?
Mm-hmm. So the way that people normally do this on a lab scale is with a microfluidic chip. Then when you scale it up to doing, you know, say a clinical trial, you can just put many of those chips in parallel with different to scale up, you know, the liters per minute that you can make. And the pharma companies really actually use like slightly different technologies. So actually, I think all of the clinical trials for RNA vaccines, the material for that was made where we formulated our RNA vaccine, which is a company called Polymoon in Austria. And they use just like a simple T-junction mixer. So it doesn't have a chip like you might see on like the precision nanosystem system, if you're familiar with that. So That's what everybody was doing to make this initially. I know when Pfizer then scaled that up to an even larger production, they use what's called a jet impingement mixer, which is basically like high pressure liquids mixing together to make the lipid nanoparticles. So there's all different processes that you can do that. I think it's an area that's still like really in development at this point.
Any other questions? Your Anna will be around for a while,
Mhm.
so we can give you a bag of CBR.
Oh, thank you.
You're welcome.
Thanks so much. And thanks everybody for the discussion. Yeah, I'll be around for the posters and the beer, so feel free to come up and ask me if you have any other questions.
Okay, great. Thank you very much. Now we're going back outside to the posters, and so you can go chat up people and their posters and do what you'd like to do. Get a drink. There's food out there.